So today is actually going to be probably our most important session. So feel free to ask questions in the chat at any time. So as soon as something is not clear to you, just ask in the chat. It's really important that you understand everything I'm talking about today, because all of the future sessions will build upon this one lecture. Okay, so we're going to start writing smart contracts actually, and we're going to start working with Ethereum today. So in the last session, I talked a little bit about this idea that we're going to deploy code on the blockchain. And then we said that the pieces of code or the smart contracts can also own money and transfer money and things like that. And we will see a lot of examples of this. But one important difference that we have in Ethereum in comparison to Bitcoin is that I can no longer really talk about coins or unspent outputs of transactions or that kind of thing. Because basically I want to have pieces of code on the blockchain, and I want these pieces of code to own some amount of money, right? So I want to have a balance for each one of my smart contracts. And the idea is that everyone on the network is supposed to keep track of every balance and the balance of every contract. So it becomes a little bit too hard to use the same accounting method as in Bitcoin, where we had unspent transaction outputs. So instead, we just say we have a bunch of accounts, and each account has a balance. And everyone on the network keeps track of the balance of every account. And now these accounts are not necessarily just contracts. We can actually have two types of accounts. And this is from the official Ethereum documents. So you can just search for this URL. So we actually have two types of accounts. We have what we call externally owned accounts. And this is basically the type of account that you know from Bitcoin. It's like someone who has a public key and they have the corresponding private key, and they can transfer or create transactions using the private key. So whenever someone wants to create transactions on behalf of an externally owned account, they have to provide the signature using the corresponding private key. And then we also have contract accounts. And the idea is that whenever you put a contract on the blockchain, you are also automatically creating an account for that contract. And then again, remember that all accounts can have balances. So you have a balance yourself, and the contract that you create can also have a balance. And they generally have the ability to receive, hold, and send Ether and other tokens. We mostly care about Ether. We don't really care about the other tokens at this point. And they can also interact with each other and with the smart contracts. But now a very important difference is that, and this was a design choice that was made very early in the design of Ethereum, is that the contracts cannot actually initiate any action on their own. So every transaction has to start with an externally owned account. Every transaction has to start, let's say, with a human who actually starts by calling, let's say, a function of a contract. Okay? So you can, again, read this documentation here. They'll tell you all the differences here. So for example, another difference is that if you want to create an externally owned account, you're basically going to just create a public key, private key pair on your own, so it doesn't cost anything. But if you want to create a contract account, you have to actually put the code of the contract on the blockchain. And we've seen that to do anything like that, you will need to pay transaction fees. And we will actually talk a lot about transaction fees today. So creating a contract account actually costs something. And of course, the most important thing here is that externally owned accounts can initiate transactions. So you cannot have a contract that just calls another contract without it being called itself in the first place. Everything always starts with an externally owned account calling a contract. And then if an externally owned account calls a contract, that contract can call another contract, and this can go on. Okay. And yeah, so you can read everything here. You can read all the technical details. I don't really want to go into all of that right now. Instead, I actually want to talk about the language that we use to write our contracts. And also I want to talk about transaction fees, because transaction fees, or what we call gas in Ethereum, are completely different from what you're used to in Bitcoin. So first of all, how does the language work? Well, we have something called an Ethereum virtual machine, or EVM. And this is pretty much like JVM, the Java virtual machine. If you've worked with that before, you would probably know how that looks like. But I can just show you some examples. Okay, let me see. Yeah, so this is basically a language that is very much like assembly. It has a bunch of operations that you can use. So this is the list of all the operations. And by the way, this is called the Ethereum beige paper, and you can just search for it and find it. It has all the technical details of Ethereum. So basically, we have a language that is very much assembly-like, and we have to write all of our contracts in this language. And these are the operations that we have in this language. So now, if I want to give you an overview of how things are going to work, you can write contracts in this language, and this is a very well-defined language with complete semantics, meaning that there is never any kind of doubt about or ambiguity about how a program has to be run. So everyone on the network can agree on the result of the execution of a program. Now, we will write our contracts in this language. Now, I'm going to have many different types of transactions. In Bitcoin, when I had a transaction, I could just send money to someone else, right? That's because in Bitcoin, I basically only had this first type of account. But now here, since I also have the second type of account, which is a contract account, I can actually do different things with the transaction. I can, of course, transfer money just as in Bitcoin, but I can also deploy a contract. So I can write a contract in this language, and then I can create a transaction that contains the code of that contract. And when I send that transaction on the network, the code of the contract is part of the transaction. So when the transaction is mined and added to the consensus chain, then everyone on the network can see the code of this contract. Okay, so that's another type of transaction that I can create. It's just a deployment transaction. And then when I have a contract on the blockchain, of course, this contract has, let's say, an address, a hash that I can use to point to this contract. And so now I can create other transactions that actually call the functions of this contract. So I can create a transaction that says, hey, I want this particular contract, and I want to call a function by this name, and here are the parameters that I want to give to this function. So I have now three types of transactions, basically. I have the normal transfers as in Bitcoin. I have transactions that deploy a contract, and I also have transactions that call functions of a contract. And when I do transactions of the third type, when I actually have a transaction that calls a function of a contract, what happens is that transaction gets mined, added to the blockchain, and as soon as it's added to the consensus chain, then every node on the network runs that function call. And based on that, every node on the network updates everyone's balances, and they reach a consensus about what we call the state of the world. And the state of the world means what are the balances of all the accounts, and also what are the values that are saved in every contract. So that's the kind of consensus that we're reaching in Ethereum. Okay. But now a very simple problem that can happen here is that, well, if I call a function, I just said that everyone on the network has to run it when it's added to the blockchain. So what if I'm some malicious actor and I just write a function that never terminates? Let's say I just write an infinite loop. I can definitely deploy a contract that has an infinite loop. That's not a problem because the code of the contract is finite, right? So I can just put the code on the blockchain. And then I can create a transaction that calls that function. But then the problem is everyone on the network has to execute it. So the entire network will be stuck, and this would be like a denial of service attack. Now, to avoid this, we have something called gas. And the idea of gas is actually very central to Ethereum. And as far as I know, all the other programmable blockchains, all the blockchains that have smart contract functionality are also using gas, and they use similar formulas as in Ethereum. So the idea here is that in Bitcoin, when you wanted to do a transaction, you had to pay a fee, right? And the idea of a fee in Bitcoin was that it's an incentive for the miner to put your transaction into the blockchain. But now we want to use the fees in Ethereum for two reasons. We want to incentivize the miners, but we also want to disincentivize computations that take too much time or too much memory. So we're going to say that the amount of fee, the amount of transaction fee that you pay is not only dependent on what you choose, it's also dependent on how much computation your transaction actually has to do. So for example, if you want to deploy a contract on the blockchain, and let's say your contract is, I don't know, 2 kilobytes, you have to pay for that 2 kilobytes of storage because everyone else on the blockchain has to actually store your contract. So you have to pay for storage. And you pay for that in your transaction fee. Now, if you call a function of a contract, that function is going to cause some execution that everyone has to do. And based on how much time or how much resources that execution actually uses, you have to also pay a fee for that. And these fees are what we call gas. So gas is basically the amount of money that you have to pay for the execution of your particular transaction. And gas is always paid by the person who's initiating a transaction. And remember, only externally owned accounts could initiate the transaction. So a contract cannot initiate something on its own, so a contract never has to pay for gas. Externally owned accounts can initiate transactions. They have to pay for the total gas usage of their transaction. Now, how does this actually work? Well, if you come back here to the technical specification in the beige paper, you actually see that in our language, in our assembly-like programming language, we have these different opcodes or operations, and each one of them has a predetermined amount of gas. So, for example, stop just ends the execution, and this doesn't actually use any gas, but adds 2 integers, and it uses 3 units of gas, whereas multiplication uses 5 units of gas, and so on. So there are many operations here. There are all the usual operations that you would expect. So addition, multiplication, subtraction, division, bitwise operations and or XOR, comparisons. And for each one of them, you have a well-defined amount of gas. And this is part of the blockchain protocol. This is part of the Ethereum protocol. So these gas prices are basically hard-coded, and everyone on the network is following the same gas price. And you have some operations that do more interesting things. So you have an operation, for example, that computes a hash, a specific type of hash, and this uses 30 units of gas. You have operations that give you information about the environment, about the status of the blockchain right now as this code is running. So you can, for example, check the balance of an account, or you can check who's calling this function. And all of these are operations that are defined in this language, and each one of them uses some amount of gas. Okay. You can also get some information about the current block. So you can ask, what is the hash of the current block? Who's the miner of the current block? That's called Coinbase. What's the gas limit? Things like that. So there are many operations here, as you can see. I'm not going to go through all these operations because actually we are not going to code in this language, as you will see very soon. But the important point here is that you have a well-defined amount of gas for each one of these operations. So whenever you do a transaction, your transaction is going to cause some of these operations to be executed. And then every node on the network is running all of these operations. So every node on the network can keep track of how many units of gas your transaction is using overall. And then they're going to charge you for that many units of gas. But how does it work exactly? Well, let me first tell you how it used to work, because that's much more intuitive, but then I will tell you how it works recently. So before August 2021, the way it worked was that you could say how much you're willing to pay per unit of gas. Okay. And you could also say what is the maximum number of units of gas that you're willing to pay for. So you could make a transaction and you could say that I'm willing to pay for up to 21,000 units of gas. And remember, this is how many units of gas every operation uses. And then you could also say, I will pay this much for each unit of gas. And this is like in Gwei, they use some weird units. So like an ether is this many V, this many Wei, and so on. And they have different names. It's just a unit. So you can say that I'm willing to pay at most 21,000 units of gas, and I'm paying to pay 200 for every unit. Now, what does happen in practice? In practice, when your transaction gets on the blockchain, everyone starts running your transaction, and everyone keeps track of how many units of gas you're using. And let's say that you used some particular amount of gas, then they're going to take the amount of gas that you used and multiply it by the price, and that's what you're paying. Okay? But now, recently, they've actually changed that a little bit. And the idea here is that you cannot just choose how much you pay for each amount, for each unit of gas. There's actually going to be a base fee, which is chosen by the network. And then there is going to be a priority fee, which is what you choose. Or this priority fee is also sometimes called the tip. So they will take the number of units of gas that you used and they multiply it by the sum of the base fee and the priority fee, and that's the transaction fee that you will pay. Okay? Now, previously, again, all the transaction fee that you paid used to go to the miner, but now actually the transaction fee you pay, part of it goes to the miner, so the priority fee part goes to the miner, but part of it is burned. And by burned, I just mean that the money will not go to anyone. So this is just some strange decision that they made recently to make sure that they don't have too much inflation in the network. But at the end of the day, what you have to know is that you, as the person who's creating the transaction, you get to choose two things. You get to choose how many units of gas you're willing to pay for, and you get to say how much you're willing to pay per unit of gas. Okay? And then it will be executed and you will pay the gas amount. Now, of course, a question here is, what happens if I run out of gas? What happens if I say I'm willing to pay for 21,000 units of gas, and then my transaction actually needs, let's say, 50,000 units of gas? Well, in that case, everyone on the network will only run your transaction up until you run out of gas, up until the limit that you set, which is 21,000. And if the transaction runs out of gas, that's an exception. So you will lose your gas money, but the transaction will be reverted. So everyone on the network will just assume that this transaction did not exist in the first place. So all the effects of this transaction will be reverted. If this transaction changed the state of a contract, that will be reverted. If it changed the balances of some accounts, those balances will be reverted. So the only change is that you will lose your gas money. So you have to be very careful to set your gas limit correctly and make sure that you're setting an amount that you will not exceed. Okay. But as I said before, we're not going to actually code in this really hard to understand language. This is basically a variant of assembly, so it's not human readable. We don't want to code in this language. But of course, all the smart contracts that are on the blockchain are in this language, right? And the reason for that was because we wanted to have a language that everyone could agree on, and we could just write all of our smart contracts in this language, and we could be sure that there is no ambiguity in the execution of the smart contract. So this is the language of the blockchain. This is the EVM. But actually, in practice, we write our contracts in human readable languages, and then we compile them. So very much like how you write a program in the real world, you will write it in a much more high-level language. Then there is a compiler. The compiler basically transforms your code from the high-level language to this assembly-like language. And then you get the compiled code, and we usually use the word compiled code or bytecode for the code that is written in this language, and we usually say source code for the code that is written in the high-level language. So you write the source code, you compile it, you get the bytecode, and what you actually deploy on the blockchain is the bytecode. So only the bytecode goes on the blockchain. Okay, but now let me actually, after this really long introduction, let me actually show you how this works. So I'm going to use this IDE throughout this course. This is called Remix. It's an IDE created by the Ethereum Foundation. You can also use Remix, or you can just use plugins for any IDE that you like. So I'm going to start writing contracts here. And the language I'm going to use is Solidity. So Solidity is actually the most common programming language for writing smart contracts on Ethereum. And you can just go on this website to learn more about Solidity. I'm actually not going to teach you too much about the language. In this course, we're actually more interested in security vulnerabilities and how to avoid them, how to find them, things like that. So this is just a distraction. We just need to learn a language in order to be able to talk about the things that we want to talk about in the next sessions. Okay. So let me actually create maybe a new file here. I'm going to call it my contract, and it's going to be .sol because that's how Solidity contracts are. So that's the file ending for Solidity. And actually here you can see some examples of Solidity contracts already. Now, the good thing about Remix is that it already has a compiler here. It compiles everything that you write. And it also has a virtualized blockchain. So it has a virtual machine where you can actually run your contracts, and you can give them tests and work with them. But this is not an actual blockchain. It's just virtualizing a blockchain. So in some aspects, this is very different from what actually happens on the blockchain, because there is no mining here. It's just simulating the miners for you. And we will see later on. So sometimes when we are talking about vulnerabilities, there are things that can happen on the blockchain that don't really happen in this virtual machine that we have here on Remix. But for now, let's just talk about our contracts. So the first thing you have to do when you want to write a Solidity contract is to set the version of Solidity that you're going to use. Okay, now why is that important? Because at the end of the day, only the bytecode is going to go on the blockchain. And if you use different versions of the Solidity compiler, you can actually get different bytecodes. So you want to make sure that your code is compiled using the right version of the compiler. You want to make sure that it's compiled using the version that was available at the time that you wrote it. Okay. And actually here you can see that my compiler is like version 0.8.18. So the way I can set the, let me just zoom in a little bit to make sure you can see this well. Okay, the way I can set the version of my compiler is just by this command. So I'm just going to copy this in my contract. this says that I'm fine with working with any compiler version that is at least 0.7 and less than 0.9. You can also give it a very specific compiler version. So you can say, I want 0.8.8. It's your choice. Okay. So now I want to write a contract. And the way we write a contract is actually very similar to the way that we write, let's say, a class in Java. So I would just have the word contract instead of class. I have to give the contract a name. So I'm just going to call it my contract. And okay, this is a contract now. Now, just like a class, you can have a bunch of variables. So let's say I want to have an unsigned integer, and let's say I want to call it A. Okay, now very important. This is actually similar to what you would call, this is very similar to what you would call a static variable in Java. So the value of this A is something that is subject to consensus. So everyone on the network will always keep track of the value of this variable A if I deploy my contract to the network, of course. Okay, and also whenever I write uint, the default in Solidity is that everything is 256 bits. So uint is basically uint 256. I can have different sizes. I can define uint 64 for a 64-bit integer, but let's say I have a 256-bit integer. Okay, so that's that. I can write a function. Let's say I write a function, and I call this function get. Let me first write set. I have a function set. And what this function does is it just sets the value of A. So let's say it takes another integer B, and all it does is that it says A equals B. Okay, now as you see here, I'm having a compiler error. And let's look at the error. It says no visibility is specified for this particular function. So every function in Solidity has to have a visibility modifier. So you have to say that this is public, for example, or you can say that it's internal. Now, what does that mean? They call it visibility, but it's not actually really visibility, because if you think about it, even if I have a private function, let's say I have an internal function here, or private, what's happening is that I'm compiling this code and I'm putting it on the blockchain. But everything is visible to everyone on the blockchain. So everyone else can see this function. Of course, they cannot see it in its Solidity form. They can see it in the bytecode form when it's compiled, but everyone can see it. So I don't have any way of actually hiding my functions. But what I do actually have is control over who gets to call this function. So if I say this function is public, what that means is everyone on the network can call this function. What does that mean? That means that if you are an externally owned account, if you're a human, you can create a transaction that calls the function set. Right? It also means that if you're a different contract, in your code, you can have a call to the function set. So that's what it means for a function to be public. Of course, I can also say that this function is internal. And internal means that only other functions in this particular contract can call it. Okay, so let's say for now that this function is public, so everyone can call it. And so basically everyone can set a value for this variable A. And now I can also have a function that returns the value. So I call it get, and I say this is also public. And I have to say that it returns an unsigned integer. And I say return A. Okay, so this is like the simplest possible contract that I can write. I just have a variable, I have two functions that set it and get it. Okay, now I've actually compiled it. Now, I have a bunch of warnings here. I don't really care about the warnings at this moment. So let's go here and let's see. So this is going to give me a virtual machine where I can just deploy and run my contracts and test them. Again, this is not an actual blockchain. It's just simulating a blockchain. So that's why it's so fast. In practice, whenever you do a transaction on a blockchain, you have to, of course, wait for it to get picked up by a miner and added to the chain, and you have to probably wait for verifications. You don't have any of that here because this is just a simulation. Okay, so here I have a bunch of accounts, and as you see, every account actually has an address. For example, this one starts with 5B3, blah, blah, and that's supposed to be the public key of that account. And of course, again, this is a simulation, so you can assume that I have the private keys corresponding to all these accounts, and I can actually do transactions with them. And initially, each one of these accounts has 100 Ether. That's a lot of money, but again, this is a simulation. This is not real money. So what do I have to do when I write a contract in Solidity? Well, first, I have to compile it. Here I have auto-compile, so it has already compiled it, but I can do it again. And then I have to deploy it. So if I click here, it will deploy. But what does deploy actually mean? You see, it actually says that deploy is going to be a kind of transaction. So when I deploy the contract, I'm actually creating a transaction that contains the bytecode of this contract, and I'm sending that transaction on the network using the HKUST protocol. And then I'm going to wait for a miner to pick up that transaction, which contains the bytecode of this contract, and add it to the blockchain. And then at that point, everyone on the network has the code, the bytecode of this contract. And then that code is also not changeable anymore. It's immutable from that point. So let's do that. Let's create that transaction. I deployed it. Now, here in the log, you can actually see what's happening. So this means that it was a transaction that succeeded. And if I go here, you can see that it says the transaction was mined and the execution succeeded. This is the hash of the transaction. This is the address of the account that I used for deploying it. So it was this account, C4. And now, very importantly, this account actually has to pay for gas. So if I'm deploying a contract, that's a transaction. Whenever I'm doing a transaction, I have to pay for gas. And that's why you see here that my balance is no longer 100 Ether. I've actually paid a tiny amount for gas. And before clicking on deploy, I could set a gas limit. I could set how much I'm willing to pay, how many units of gas I'm willing to pay at most. So I could put a limit on how many units of gas I'm paying. And the default limit is just 3 million. Of course, I can change that. On the blockchain, as I told you, you can also decide how much you pay per unit of gas. This is actually not available here in this Remix IDE, but just know that you can do that in the real world. So here, Remix is actually just choosing the gas price for you. But now here you can actually see how much gas you used. So this is the total amount of gas that was used, 144,000. And this is actually divided in two parts. There's a transaction cost and there's an execution cost. You don't really need to get into the details of these, but basically every transaction, just creating a transaction has a particular gas cost. And then you have to pay based on the size of your transaction. And then the execution cost is actually the gas cost that we care about more, which is the cost of running your code. Okay. And you might think that, well, I didn't actually run any code. I just put this code on the blockchain. So why do I have an execution cost? Well, because your code has a variable. So when you're putting this code on the blockchain, you're also telling everyone on the blockchain that, hey, you have to keep track of this value of A. And of course, initially it's 0. So just creating that value of A and setting it to 0, which is something that is done under the hood and you're not seeing here, that causes 67,000 units of gas to be used. So you have an execution cost. But anyway, what I want you to see is that you need 144,501 units of gas to deploy this particular contract. Now, what happens if I pay less than this? So let's say I use a different account. Let's say I use the second account and I set my gas limit to 5,000. Okay. Oh, and by the way, when I deployed this contract before, I can then have it here and I can work with it. But let's say I want to deploy this contract with a gas limit of only 5,000. So I'm paying only 5,000 units of gas for the transaction that is deploying this contract. I click on deploy. Oh, what happened? Why did it succeed? Okay. This should not succeed because it's actually, okay, this should be a bug in the, oh, it's not applying the gas limit. Okay, so this virtual machine actually has a bug and it's not really applying the gas limit right now. So what would happen on a real blockchain is that you cannot spend this much gas because this is more than your gas limit, and then your transaction will fail and your contract will not be put on the blockchain. But here again, the virtual machine has a bug. Okay. Anyway, let's go back. So let me just remove this and let's do this again. So I'm going to set my gas limit back to 3 million. And I'm going to deploy this again. So when I deploy my contract and when it succeeds and gets added to the blockchain, I can now interact with my contract. But very importantly, every contract is an account and every account has an address. So here you can see that this is a contract that has an address, and I can actually click here to copy the address. So the address was this. So since now this contract has an address, I can create a transaction that points to this contract using this address and then calls one of its functions. But other than that, this contract also has a balance. And as you see right now, the balance of this contract is 0. Okay, because I haven't sent any money to this contract. So now let's actually do get. So let's say I use this third account and I call get. Again, as you see here, I paid for the gas, right? Because calling a function is also a transaction. You have to pay a transaction fee. You have to pay for gas. You have to pay for every operation that happens here in get. And again, you can see the details of how much gas it used here. Okay. Now I can also use set. So let's say I want to set the value of A to 500. I do this and I click on set. So here what I'm doing is, again, I'm creating a transaction that has a pointer to this contract. It has the address of this contract. It has the name of the function set, and it has the value of 500. And when I do this, again, everyone on the network, when the transaction gets added to the blockchain, everyone on the network runs it. And so after this point, everyone on the network knows that the value of A in this particular contract at this address is 500. Okay. And again, you can see how much gas it used. So let me try again. Let me try to set it to 600 and let me give it very little gas. Hopefully this time it will fail. So I'm just giving it 5 units of gas and I'm calling set. Okay. Again, something is very wrong here because this should not work. But yeah, this, so I'm saying my gas limit is 5, but it's actually using much more than 5 units of gas. This will not happen on the actual blockchain. Okay. So I don't know what's wrong with this. Okay. So I have this contract and I can do all of these things. And as you saw, every one of these operations creates a transaction, and I have to pay for every one of these transactions gas usage. Okay. Now, what else can I do? Well, of course, what's really interesting to me is that I want to be able to talk about other people and other accounts in my contract. So I want to be able to point to an account in my contract. So let's say I have an address, and this is a data type that exists in Solidity. And I can create an address and I can call it, for example, let's say owner. So this would be the address of the owner of this contract. And I can say that the owner of this contract is, let's say, this account. So I can just copy the address and put it here. So we have all the normal data types like integers and strings and all sorts of things like that, but we can also have variables of type address, which basically tell us who owns or who, which basically let us point to a particular account. In this case, I want to say who owns this contract. I can also have a constructor function. So I can have this, I can have constructor. And of course, the constructor will be called whenever this contract is deployed. So constructor is a function that is only called when you deploy it. Okay. So let me see. So here I'm going to say the person who deploys this contract is supposed to be its owner. So how can I say that? I can write something like this. I can write owner is msg.sender. Now, what is msg.sender? msg.sender, whenever you have a function, msg.sender is the person or the account who has called this particular function. Okay, so in this case, since my function is the constructor, msg.sender is whoever is deploying this code on the blockchain. So what this code here is saying is whoever deploys me on the blockchain is the owner. Okay. And by the way, I can also add public here so that anyone can ask for the owner later on, but of course they cannot change it. So let me deploy it using this one. So remember, there is F2 at the end of the address. So I deploy, and here I have this contract, and I can ask who's the owner, and actually the owner is the one who deployed it, F2 at the end of the address. Okay. Nice. So we can do all of these things. Any questions until now? Okay, if no questions, then I'm going to actually go forward and let's do some more interesting things. So let's say that I want to actually send money to this contract. So how can this contract receive money? Well, one way of receiving money is that the contract can have a function that is payable. So let me remove this. Let's say I create a function, I call it pay me, and it's public, but I also say it's payable. Payable means that whenever you're calling this function, you can also include some money that will be paid to this contract. Okay, and let's say this function doesn't do anything, so it's just used to pay the contract. So I'm going to deploy this contract. Now I have this contract, and let's say I change my account. Let's say I go to this one, which had 100 Ether. And here I can set the value. I can say how much I want to pay. Let's say I want to pay 5 Ether to this contract. Okay, so I set the value to 5, and I call the pay me function. So now here several things happened. Well, first of all, this was a transaction, of course. So it called this function, and this transaction was mined as usual. It used some gas and so on. You can see the log here. But importantly, it took 5 Ether from the account that was calling it and gave that to the contract. So now the balance of my contract is 5 Ether. But the balance of the account decreased by more than 5 Ether because the account had to pay 5 Ether to the contract, and it also had to pay for gas. So that's why my remaining balance is not 95, it's 94 point some 99 blah blah. Okay, so now this contract has 5 Ether. But this is one of the most common mistakes that you can make. So I have no way of getting this money back from this contract. Because if you look at all the functions that I have in this contract, none of them pays back the money. So I've just sent 5 Ether to this contract, and that 5 Ether is basically lost forever. There is no way I can get it back. Because the only way you can get money back from a contract is if you call one of its functions and then the code reaches a place where it pays you back. So, and changing the code here doesn't really help because I've already deployed this contract, and so this is the version that was deployed, and I cannot change the code of what's deployed on the blockchain. I can, of course, write a new contract, but these 5 Ethers, they're owned by the previous version of the contract, the version that I put on the blockchain, and that version didn't have any facility for getting the money back. So that money is now gone. Of course, thankfully, we were in a virtual machine, and I didn't really lose 5 Ether in the real world. Okay. So let's get rid of this contract. And oh, by the way, when I'm getting rid of these, I'm just removing them from my virtual machine. In the real world, of course, you cannot remove a contract from the blockchain because a contract is part of a transaction. If the transaction is in the blockchain, it's immutable, it will never change. So when you deploy a contract to the blockchain, it's there forever. Okay, let's do something more interesting. Let's say I want to have a contract that has an owner, and let's say anyone can pay this contract, and only the owner can get the money back from the contract. So here's what I'm going to do. Let's just have the same thing as before. I don't care about this one. Let's say I have an address of the owner, and my constructor just says the owner to whoever is deploying this. And then I will have a function. I call this pay me. And this function is public and it's payable, so anyone can call it. You just pay the contract, it doesn't do anything at the moment. And then let's say I have a function called sweep, which pays the entire balance of the contract to whoever calls it. Okay, so this is public. This is what I'm going to do. I'm going to say, take whoever is the sender of the current message, so whoever called this function, and transfer all the balance of the current contract to that person. So I'm writing a very stupid contract. It's a contract where anyone can call in and take the entire balance of the contract. Okay. Now, in order to do that, I have to first tell you the difference between address and address payable. So in order to make sure that you don't pay someone inadvertently, in Solidity, we have address and we also have address payable. And address payable is a different kind of variable. It's a different type. And the idea here is that you can only send money to an address in your contract if it's of the type address payable. So I can create an address payable, and let's say I call it receiver. And I'm going to say receiver is going to be the person who called this function. So msg.sender. but I have to convert the type to payable. So I have to do it like this. Okay. And then I say receiver.transfer. And this is how a contract can actually transfer money. And I can say how much money I want to transfer. So I can say 1 Ether, for example, right? So let's just do this. What is the error here? Okay. Let's say I'm just going to transfer this much to the receiver instead of 1 Ether. So let's see what happens. So I'm going to deploy this contract, and I'm going to deploy it using this account. So I deployed it. The contract is there. Now I'm going to pay it, let's say 50 Ether. Okay, 60 Ether, let's say. I paid 60 Ether. Now the balance of the contract is 60 Ether. Now anyone else, for example, this account can come in and they can call the function sweep. And when they do that, the balance of the contract goes down by this amount. And by the way, all of these amounts are in our smallest unit, and our smallest unit is this one, VEI. So this is our unit here. And this person is actually paid that much. Okay, great. So now I have a contract that can send money. But how can I say that I want this contract to send its entire money? Well, I have to somehow get the balance of this contract. Now, the way I can refer to this contract is that I can just write this, right? So very similar to how things work in C++ and Java. So I say, take this, convert it to an address, and then take its balance. So this is going to give me the balance of the current contract. And so now what this function sweep does is that whoever calls this function takes all the money that belongs to the contract. So the contract will send all the money that belongs to it to whoever calls this function. Okay, let's do this again. Let's say again, I deploy this new version of my contract, and let's say I give it 50 Ether. So now it has 50 Ether, and now someone else comes. So let's say this account comes, and he calls sweep. And as you see, the balance of the contract becomes 0. The balance of the account was increased by 50, but of course, not exactly 50, because again, it had to pay for gas. But right now, all the money in this contract went to that account. And again, you can see all the details here in the transactions that are happening here. And it's giving you a complete log of like how much gas was used and how much gas was used for each type of operation. Okay. Now I can also use other things. So for example, I can take the block hash. I can look into things like that. These are actually called global variables in Solidity. So if I just search for global variable Solidity, it will give me a list. Okay, so these are the things that you can actually use here. So you can use block hash, you can use block.coinbase, which gives you the address of the miner. So if you want to just pay the miner, I don't know why you would want to do that, but you can do that. If you want to, let's say, bribe the miner, you can just say block.coinbase.transfer some amount, right? You can get your block number. So you can see what the current block number is. You can see how much gas is left. You can see who sent the current message. So who called the current function. You can see how much money was sent. you take something called now, which gives you the timestamp of the current block. You can ask for the gas price in the current transaction. Oh, that's actually what we could not set in this virtual machine, but we can ask for it. So that's nice. So let's say I have, let's do this. Let's say I have a uint A, and when I call pay me, I set A to be the gas price. So TX that gas price. So I can see how much I'm actually paying for every unit of gas. What's happening here? Type is not callable. Oh, sorry. It's just TX.gas price like that. And let's say this is also public. Oh, and by the way, again, this public or private or whatever you write here, it doesn't really affect the visibility because everyone on the network is going to keep track of all of your variables here. So everyone can know the value of all the variables. But when I say it's public, it just means that other contracts can access it. And if it's not public, then other contracts cannot access it. Okay, so I'm going to, again, deploy this. And so I'm going to pay it, let's say 1 Ether. And now I can see what the value of A is. Oh, and actually the value of A is just 1. So in this simulator, the gas price is always set to 1, but of course that's not the gas price in the real world. Okay. But one really important point here is that you have two different things that you should know are not the same. One is msg.sender. And msg.sender is the address of the account that is calling the current function. And then you also have tx.origin, and that's the origin of the transaction. That's the person who created the transaction in the first place. So tx.origin is always a normal account. It's an externally owned account. It can never be a contract. Now, the way you can think about it is that maybe I create a transaction that calls contract A, some function in contract A, and that function calls some other function in contract B. Then in that function in contract B, msg.sender is contract A, but tx.origin is the original caller, it's me. Okay, so you have to be very careful about the differences between msg.sender and tx.origin. But generally, if you just search for variables, Solidity, global variables, you can find a list, and actually you can check all of them. Okay. So let me finally give you an example of kind of a really stupid contract, but something that was famous for a while. And this contract was called King of the Ether Throne. So it's a very simple contract. It's actually a Ponzi scheme. The way this works is that you can pay to be declared king. So there is an address, and this is the king. The idea is that you just want to show that you're really rich, so you can pay this contract to become king. And the way it works is that you have to pay more than the previous king. And when you pay more than the previous king, your money is actually sent to the previous king. Okay, so we have a king, and we also have a price. This is the amount of money that you have to pay to become king. So I have a constructor. I say that originally king is msg.sender. Or I can say king is tx.origin in this case. So whoever is deploying is going to become king. But now, as you see here, I have an error. And the error that I have here is that it says tx.origin is an address, but king is an address payable. So you cannot just convert easily, you have to convert explicitly. So you have to say, I want to make this payable. This is just a check to make sure you know what you're doing with your money. Okay, so I set my king to be whoever deployed this contract. And initially I set my price to 0. Of course, I don't need to write this because that's the default behavior anyway. But okay, let's say this is my constructor. And then I can have a function that pays this contract and tries to become king. So I can have something like this. I can say, let's say I have a function become king. And this function is public. Anyone can call it. It's payable. You can pay money to this contract while you call this function. And what this does is that if the amount of money that you paid, if msg.value, this is the amount of money that was paid to this function. If this is more than the price, then we change the king. So we say our new king is actually msg.sender. Okay, again, I have to make sure that I'm doing a typecast. So this is my new king. And what is my new price? My new price is msg.value. And of course, before doing all of this, I want to pay the previous king. So I say king.transfer msg.value. Okay. So kind of a very stupid contract, but it actually worked in the real world. I'm going to change it a little bit in a moment. But basically, you can pay this contract, and if you pay more than all the previous people, then you become king, and everyone can see that you're rich and you're king. Okay, so let's say I just deploy it. So this is deployed. I can check who the king is. The king is the one whose address ends with 54C, which was, of course, the person who deployed it, because that's what happened in the constructor. And now let's say I want to call become king. Oh, I forgot to make the price public. So let's do this again. Let's deploy it. So originally the king is the person who deployed it. The price is originally 0. And now I'm going to say, let's change accounts. Let's say the person with this account comes and they pay 2 Ether to become king. Okay. Okay. Now, what happened here? Well, first of all, the balance of the contract remains 0. This is because 2 Ether was paid to the contract, but the contract immediately transferred it to the previous king. So you can see that the balance of the previous king went up by 2. Okay, and of course, the balance of this new king went down by 2, and also the transaction fees. Now I can ask who's the king, and the king is this new person. I can ask what's the price. The price is now 2 Ether, but all these prices are in VEI, which is like the smallest unit. Okay, but now what happens if, again, I do something stupid? What happens if I take another account, let's say this person, and let's say that this person didn't know about the previous transaction, didn't know that someone else has created a transaction and they became king by paying 2 Ether. So maybe this person wants to pay only 1 Ether to become king. And so they call become king. Ooh, now a really bad thing happens. So our king did not change, but I paid 1 Ether to become king. All that did was give that 1 Ether to the contract. So now the balance of the contract is 1 Ether. But then this if condition was not satisfied. So nothing was transferred out of the contract, and the king and the price did not change. So you see, the problem with this contract is that it has a race condition. If I have 2 people who want to become king at the same time, let's say, and one of them creates a transaction to become king by paying 1 Ether, and the other one creates a transaction to become king by paying 2 Ether. Now, if they do these transactions at almost the same time, it's completely up to chance which one of these two transactions is going to be seen by the miners first and mined first and put on the blockchain first. So if the transaction that was paying 1 unit to become king is seen first, then that person becomes king, and then comes the transaction that was paying 2 units, so the king changes, and the guy who paid 1 unit will not lose any money because they will get their money back. But if the order changes, if first the transaction that was paying 2 units goes on the blockchain, and then the transaction that was paying 1 unit, then I have a problem like this. The transaction that was paying 1 unit is just paying 1 ETH. That 1 ETH is going into the contract. It's part of the balance of the contract now, but that person did not become king, and there's no way for them to get their money back. So you have to be very careful when you write contracts to make sure that you do not create race conditions like this. Okay. We have a question in the chat. In what aspect does it make a difference whether a variable is private or public? I'm asking because the variables can only be changed through a function. If you don't specify the public private to a variable, what is it? Okay, so the variables are private by default. And the reason this actually matters is very much like the functions. So if you have a private function, everyone can still see the code of this function. But another contract, a contract that is not the same as your current contract, cannot actually call this function. Okay? So similarly, if you have a variable that is private, even though it's private, I mean, then the name doesn't really mean anything. Everyone can see the value of that variable because that variable is saved on the blockchain. So if I say this king is private, still everyone can see it. But the important point is that no one can write a contract that actually uses the value of your king in that contract. So it's private to other contracts. It's not private to people who are seeing the blockchain. That's the difference between public and private. Okay. So how can I fix this particular contract? Well, instead of saying do this only if this condition is satisfied, I can write what we call a required statement. So I can do it like this. These are spaces. I can say require MSG.value to be more than the price. Now, what does require do? Well, when this function is called, this requirement is going to be checked. And if this requirement is not satisfied, that throws an exception. And when an exception is thrown, the entirety of the transaction is going to be reverted. So anything that happened as a result of this transaction will go back to the state before this transaction. The only change, of course, will be that the person who called this transaction has to still pay for gas. Okay? So here's the thing. Let's say I have another integer. And let's say I call this updates, which basically just keeps track of how many times the king has changed. Okay, and I can say when you call become king, updates increases by 1. And then I check that the amount of money that you have paid is more than the price. And if that's not the case, I would revert the entire transaction. If this requirement passes, then I'm going to transfer this money to the previous king, and I'm going to make you the new king, and I'm going to, of course, update the price. Okay, so let's say now this account is going to deploy the contract. So the contract is now deployed. And now let's say that this account wants to pay 2 units, 2 Ether to become king. Okay, so now if I ask who's the king, this is the king. the account that paid to 2 units. What's the price? It's 2 Ether. And what were the number of updates? Just 1. And now let's say that this account comes in, and let's say that they pay 5 Ether to become king. So become king. The king changed. The price also changed. And the number of updates is also now 2. And of course, you can see that the balances, this one lost 5 and this one gained 5. Okay. Now, at this point, let's say that some other person comes, and let's say that they want to become king by paying only 4 Ether. And that's, of course, not going to happen, right? So they call become king, and they pay 4 Ether. Let's see what happens. Well, first of all, you see that the transaction actually failed. So let's look at this log. It says transaction mined, but execution failed. So what does this mean? It means that your transaction was actually picked up by a miner. Of course, again, this is a virtual machine, there is no miner, but this is what would happen in the real world. Your transaction was picked up by a miner and it was added to the blockchain. So everyone on the network actually executed your transaction. But what happened in that execution is that, well, it first increased the number of updates, and then it got to this require. But when it got to this require, the condition was not satisfied. So the transaction got reverted, which means that any changes that this transaction made to the state of the vault, to all the variables in this contract, to all the balances before this require happened, will also be reverted. So now if I ask how many updates I've had, it's still 2. So even though this transaction first increased updates to 3, because it then failed this require, all of its side effects were reverted, and so updates is again back to 2. So the only side effect of this failed transaction is that the person who initiated the failed transaction had to pay for gas. And actually, if you look at the balance of this person, you see that the balance is decreased only by the amount of gas, even though we said that they pay 4 Ether to call become king. So even the changes in the balances are reverted. So that's how we make sure that our contract doesn't do anything stupid. We can just use a lot of requires. Now, another way that we use require usually is that we want to maybe do access control. Maybe you want to make sure that a particular function can only be called by the owner of the contract, okay? Or, yeah, so I don't know. Let's say I have something like this. I have an address called owner, and I have a function f. I want this function to be public, but let's say I want only the owner to be able to call this function. So I can just add a require at the beginning of my function, and I can say require msg.sender to be the owner. And that makes sure that if anyone else calls this function, then this requirement will fail. And since this requirement fails, their entire transaction will be reverted, so it will have no effect at all. Okay. Now, by the way, these things are authenticated by default. So when you're creating a transaction, you need to sign that transaction. So you cannot fake a transaction from someone else. So I'm pretty sure that msg.sender is the right value. So if msg.sender is the owner, it really means that the owner created a transaction that was calling this particular function f. Okay. I want to also show you another small thing here. Let's see what happens if this contract tries to pay out more than its balance. Okay. So this function become king. What's happening here? It's getting some value. So that's the amount of money that was paid to the contract. So that becomes the balance of the contract. And then the contract is transferring exactly that value to the king. But what happens if I want to transfer more? MSG.value plus 100. So my contract does not have this money. Let's see what happens if it tries to actually transfer money that it does not have. So I deploy it. Let's say I want to become king by paying 5 Ether. So look at the balance here, it's 99 something. So when I click on become king, I'm sending 5 Ether to this contract. And as you see, my balance did not change. So this is another case of an exception happening. So the contract started executing, it got to this transfer, but it did not have enough money. So there was an exception. And when this exception was thrown, the entire transaction was reverted. So the person who created this transaction only paid for gas, but all of the other side effects of the transaction were reverted. So you see, this is actually something that we will come back to in later sessions. Sometimes your contract has a bug that basically disables a particular functionality. So if you have a bug like this, it's just like saying no one can call become king, because anyone who calls become king at this point, their transaction is going to get reverted, right? And they're just going to waste some gas money. That's right now, that's all this become king does, just because of this bug here. So you have to always make sure that you don't transfer more than you have, because of course we cannot create money out of thin air. Okay. Let me see. So what else did I want to tell you? Okay, one more important thing is that we actually have different types of variables in our contracts. So there are these variables here, and we call these usually storage variables. And these are the variables that everyone on the network has to keep track of. So this is what we call is stored in the storage of the contract. So everyone always keeps track of the value of king, price, and updates here. But of course, I can have other things. So let's say, for example, maybe this function gets a parameter A, right? So that parameter, it's not going to be part of the storage. So we usually say that A is just in the memory of the contract. Okay, and also I can have maybe some local variables in this function. Maybe I have some integer y or unsigned integer y. Again, this is a variable that exists only when this function is called. So when I call this function, this y comes into existence, and at the end of it, it goes out of existence. So it doesn't have to be saved on the blockchain. So the things that are actually saved are on the blockchain, a better way of talking about this is that the things that are saved on the blockchain are the transactions. But what are the values that everyone on the network has to keep track of? Everyone on the network has to keep track of all the storage variables or all the global variables here. But all these local variables, they have a very short lifetime. And after the execution of this function ends, no one on the network needs to remember what the value of y was. So actually, these variables are more expensive. So if you put something into storage, you have to pay for the storage. You have to pay for the amount of space that you are taking in storage. And also, if you do calculations with variables in the storage, you have to pay for gas. And generally, working with storage is much more costly than working with local variables like this, with memory variables. So a very important point when you're implementing contracts is that you want to save as little information in your storage as possible. So if you can put it somewhere else, put it somewhere else. Don't put it into the storage of your contract. Otherwise, you will have to pay a lot for its gas usage. Okay, so that's it for this session. You now know how to write basic codes in Solidity. And I mean, the language itself is not that important. What's really important here is to understand how the contract works, how the transactions work, how this really relates to the whole idea of the blockchain. So yeah, that's it for this session. I'm going to stay. If you have any questions, please write them in the chat.